Thanks very much, Quincy. So we're here to talk about how we literally are dividing and conquering the multidimensional Gordian knot. So AirMettle's analytical data platform is a software-defined platform that provides superior throughput and latency for many big data operations compared to typical things like data warehouses. We address problems in a number of different areas, including better understanding the data, which we can characterize and help visualize data using compact, efficient, multidimensional graphical histograms. This is work which we've been collaborating with Los Alamos National Labs has the potential to significantly accelerate a number of their performance problems on their post-simulation workflow. The core aspect we do is on extracting and summarizing data, starting with event-to-record oriented data, such as you might have in security, information event management processing. This was the original grant we had for the National Science Foundation. And we've been working more recently on enabling support for scientific data, most of which, like both of my talk, we're talking about in this area, which has been supported through two grants, the National Oceanic and Atmospheric Administration. This enables you to actually efficiently store hierarchical, like not hierarchical, like climate data models, and do actual analysis in place while stored in a fully distributed manner. And the other additional thing we've been working with more recently is having the ability to execute user-defined functions to potentially even look at data on arrays and potentially even AI to be able to process data and to help accelerate labeling of data for clients. So it's these last two which support multidimensional data, which I'll be talking about today. So, of course, like in this day and age, you really need to step back and think. Like, you've seen the scale of these supercomputers that people have that we're making in this day and age. And you really have to wonder, why is big data so slow? Like, how is it possible that we have things the size of professional sporting event stadiums and larger, and data set that do basic data operations is so horrifically slow? Well, you go back to the first principle. What's going on? Like, how are you storing your data and how are you protecting it? A lot of basic data protection is using RAID or erasure coding, and these algorithms, well, like if you, like probably as a rule of thumb, if you think about like how are things solved in a computing like context, you're really looking at what is the problem, what's expensive today, or what's going to be expensive, and what can you use that's cost-effective and economical to solve the problem at that point in time. Well, back in the day, it turned out that wires were relatively expensive, or wires were relatively cheap. I mean, you could get people and have them wire wrap things, okay, because wires were cheap. Like, yes, people wire wrapping things was cheap. Why? Because gates were horrifically expensive. So the data protection algorithms we had unexpectedly had very compact, efficient things like XOR on a large set of stuff, and you had to move all the data. So we just keep moving all the data. Like, last time I checked, there's more compute power on my wrist than the entire planet had to put a man on it. The problem isn't, like, computing is incredibly expensive. The data movement, like, that, in fact, is the problem. So, like, so why is it a problem if data is stored and erasure coded or, like, rate protected? Like, so why is it slow? Well, we'll get to multidimensional data. Like, look at something fairly simple. Just look at CSV data. Like, okay, this is like nice, this is very simple data from schema benchmarks. Just take a couple SSDs. Nice, fixed, uniform size, very easy. Proven data protection algorithm used for decades. So what happens? You take your data and you put it in. Oh dear God, that's a disaster. Like, you basically chop objects up into arbitrary points and cut it off, and like, you really can't do anything with it. So do we just throw in the towel and like move all the data because that's the way we've been doing it for decades? But wait, let's make this problem more challenging, more difficult, because only whenever you've added plenty of constraints, you understand that the bad solutions fall away and go up with the good ones. Let's look at multidimensional data, the kind of stuff you have for keeping climate data models. So these are complex structures. So it's, even the coordinates are multidimensional. There's a latitude table, there's a longitude table, and there's the data tables. And you need to look at subsets, like different people need to analyze different portions of the climate data, or they're looking for aggregates at different scale. And so do we generate a simulation and then compute every individual piece that anyone might want? You could. We talked to some prospects and said, like, well, how are you solving these problems today? You keep the data you collected, the simulation puts it up, or the data is collected and stored in NetCDF or HDF5. So how do you analyze this? Well, there's a lot of people that are looking at moving and replicating the data to other data formats, such as ZAR, or loading them in completely separate databases like IODB. Why are they doing this? Because it is very painful to analyze data in some of these formats. They're efficient, they're used as a format of record, but if they're not getting good performance out of it, then this begs the question, do we risk letting these data formats that you've collected and stored data in standardized formats for years, they just become like formats of record, but no one actually analyzes? You have to reload it to do any analysis. We said, we basically looked at the problem and say, we took out Occam's razor, slash Gordian's knot, and say, like, we're going to look at this problem. How do we reassess it? And how do we actually enable these data formats that you know and love and make them fast? Because that's kind of the goal. I mean, do you, like, if you already have the data collected and stored in these formats and they're useful in these contexts, can you use them to solve the action? The answer is yes. And how we do that is whenever we store the data, we don't just store it so that it's reliably stored blind. We look into the content. Now, the vast majority of data which is collected and stored today, unsurprisingly, if you have different tools that can access the same data, it's typically, yes, it will be encrypted server side. Like, we're the storage platform. We are server side. So to us, to our platform, the data is in the clear. So because the data is in the clear, we take advantage of the characteristics that any other application can, that as long as the data follows the standard data format, so it's like, it is in a CDF data type, then we interpret the data as it's coming in, and we store it aware of the boundaries of the structure. And what that enables is that we can actually segment the data so it's stored efficiently in a compact manner. It is the actual data that the clients wrote. It's not that we loaded it into a separate database. It's efficiently stored in the manner of the file type that they sent. It's readable all the time in the format that the client actually wrote the actual original data. The queries are a little bit more complex. Queries on this data type, as I'll show you in a few minutes, are 2 to 3 stages to do a query. So it's definitely more complex than you have for tabular data, like for SQL processing. But I said efficient, so you say like, well, lots of people say, oh, we just replicated 3 to 6 times. So what's our efficiency? Let's see, we took in a number of data sets from DataMap and others. Data set sizes like hundreds of kilobytes, hundreds of megabytes in many cases. And our efficiency for the overhead of enabling full in-place parallel distributed where stored processing is typically under 1%. Like, you simply don't see it. It's completely irrelevant. If you want context, your overhead for typical erasure code data protection is going to add like somewhere between 25 to like 40% overhead on top of the raw data. Say like ballpark, typically around 30%. Like, okay, so that's like we can add about 1% before you add 30%. This is not putting it into a different data format. It's not replicating it. It's very efficient and compact. So it's actual NetCDF or actual HDF5 that's deeper, and we can use it. Like, we are an object store, so we're storage, retrieval, analytics. You're not editing things like in our platform because it is an object. But now there is one thing one problem I hadn't brought up, which is that, well, whenever we partition it, it's on structural boundaries, and just like CSV, as I showed earlier, they're not fixed size. So, Okay, so the algorithm is a little bit more complex for the erasure. You have time on that, so it works. Like effectively, you take in a protection group, from largest to smallest, effectively in a small group, you sort them, and then the code algorithm changes. The number of data elements changes so that from max to min. So you don't need to store white space or whatever in the things once you've written the data. Like the protection code numbers remain the same. So straightforward with these data tables. So let's look at SCDF data. So here's an example data set. Looking at data like over most of the continental United States. You have a range of like latitude, like roughly 22 degrees range covered the country, and longitude about 56 degrees covered the vast border. So if you're looking at this from a square degree basis, like if a latitude and longitude are respectively one machine effect in parallel, you need about 30 machine equivalents that the data is stored across. Now, in reality, when the data is stored in a distributed manner, like you tend to break things up onto single-digit megabyte pieces, which is roughly on that order of scale. So you'd expect on a typical data set, you'd have tens to hundreds of, like 100-ish machines where the data is. If you want to take a simple select query, where you want to say, you just want a region of the data. So you have the entire continental United States, and you want to get a region, say, of the Northeast. So you can actually, instead of having a separate file, you can literally just request the file on demand whenever you need it. So how is that done? You literally select and retrieve the subset of the object you want. And what we do is we scan the latitude table, scan the longitude table. Those are fully done in parallel. And the results of those tables are then fed into the place where we have the data elements. We fetch the subset of the data elements you want, and then we combine it and return to the client what looks like as if you had stored an original NetCDF4 object on just that region of the country. So, like, you literally just get the piece you need on the fly. And the computing is that, like, if you think about your typical networking or like supercomputer facility, you have about as much floor space for the storage infrastructure as you do for the compute. People typically count like the compute nodes on the compute nodes, and you kind of have compute on the storage. Not doing very much. It's almost as much floor space, almost as much power. Why don't we use it? So we do. So what else? Regridding. This is something that's also fairly common. If you either simulate or you will gather data at a very fine degree, and if you're going to compare data on different resolutions, you basically will downscale it so that it's the same resolution, or you could potentially want to take data and whenever you rescale it, you might not want to rescale it to like the average. So if you're looking at zooming out to something, you normally see what the average is. But for some weather applications, you might want to get, when you zoom out, you might want to get the standard deviation, because that can give you indications of if there might be a storm front or something of interest. So we've added the ability that whenever you do a subselect, you can add the ability to regrid in a parallel manner in the system itself. And for that, we're using the ESMF, or System Modeling Framework, to do regridding. So the regrid operation works very similar to a select. It's basically, the regrid is effectively a form of an aggregate. So we do the same selection of specifying the range of latitude and longitude we want, and then like the same way that in SQL, we would say that we want to get like an average, a mean, a standard deviation. To this, we apply regrid. And regrid can also be done in a fully parallel manner in place while stored. And that looks a little bit different. Because once we do a subselect, the regrid is again fully in parallel across the system. An example of if you're looking at that on a like global boundary, this is from a water salinity model. If you want to say like take Europe, then you do a subselection for the region of interest in Europe, and you like simply do a regridding. These are just separate commands. And for large models, we typically like orient for the data set to be distributed across roughly 100-ish nodes. It's more that, like, even though the data could be distributed across more at some point, like, we think it's probably, you're reaching a point of diminishing returns for the amount of parallelism that you're getting from accelerating the problem versus the overhead of having as many nodes where the data is sort of a distributed manner. In a typical object store, you don't, like, there's a limit to how wide you spread an individual object regardless of size. And so those queries for this was selecting salinity from a latitude range between 36 and 70 degrees and a longitude between -10 and 40. And it's all pushed all the way down into the system, and only the results that need to touch the wire touch the wire. Because you might not realize it, probably some of the most expensive stuff you have in the data center is the networking, which is connecting all the dots together. The further you can push computation down, the faster the system gets, and the more power efficient the system gets. Again, both of these queries return as fully formed NetCDF4 objects. So you query it, the query is like a RESTful API, but it comes back as something you can directly process with as if it was a NetCDF4 object. That's how it returns. So next piece we're adding is the ability to in place like user-defined functions or say AI inference to find and label rich media. So last year, like we talked with people at Argonne, who pointed out that like the beamlines, they collect an enormous amount of data, and you're trying to look at, you want to apply different algorithms to look at each of the images that come off of the beamline. So you can do things like effectively find, identify, label areas of interest, and particularly when you have data sets that have like hundreds to thousands of images, like automating this can be a huge productivity boost for the scientists. So what we're adding is for this step, so the like HDF can be much more complex for the structure that are supported than NetCDF. So for this step, for what Argonne needs, they aren't actually using much of a hierarchy. It's effectively a flat stack. So we're literally taking every like array slice, and so that's basically the boundaries that we're choosing for where we can partition the data. In our system, we're now using like effectively a Docker container, so we can basically slice each image, and that is basically given to an application that's contained in Docker. So this gives us a very easy way to test, deploy. This is on the same model at scale. And support for more generic like HDF hierarchies. The overall theme here is these are proven like data models which have been widely used in the scientific community and a number of areas of years. And we think instead of throwing out these formats we don't love, it's much better to go to the root of the problem. How do we make these actual data formats fast? Integrating analytics directly with the story. So this work has been supported by grants from the National Science Foundation, National Oceanic and Atmospheric Administration, and the U.S. Department of Energy. And unsurprisingly, a number of these things look like they're patently obvious, so we are. So, any questions?
Because it's the topic of the year, probably, how would you compensate with GPU access?
So the data, since the data has been partitioned for parallel processing across the fleet, we have the ability that each of the subcomponents can actually be processed like in parallel, even delegated further. So there is some work that we're currently doing. We're expecting to be able to announce soon. So if you're looking at something like the latitude table and longitude table, so those tables are very, very simple and straightforward. We're going to be able to push the scanning of the latitude and longitude table down to a industry standard high volume production SSD. So those table scans and the results of that will be done by the actual SSD saving us in a full order of magnitude of bandwidth coming off the front.
So maybe I should think like TPU.
Yeah, so the other thing is that the more complex thing, which is taking the results of that, so the actual data table, that data could actually potentially be retrieved as the SSD can't do the filtering. We can do that to a GPU for the more complex analysis. So but every shard of the system can be separately processed. The GPU would certainly be a very high performance node for doing the more complex joint operations.
There's going to be things where you need the bigger picture.
Yeah, yeah. So would very much like to follow up with NVIDIA on that. Okay.
It's pretty interesting. And just as a note, Sandy is doing the same kind of thing internally to get performance up a little bit later. So my challenge with this kind of work, or kind of work with storage, is that the only time it happens with files is if you do it faster than the amount of transfer time saved.
Yeah.
100 gigabit interconnect. Can you get enough work done that it's not worth just transferring all the data and doing the work on the other side?
Yeah, of course. I mean, like we can, like, so if you hear the question, one of the questions on accelerators in general, and this held off like things like what is now like DPUs. DPUs have been talked about for decades because there was a question of could you offload TCP processing faster than could you get your offload engine working faster and offload the processor so that you were going to be ahead of literally what the next processor from Intel and AMD was going to have. And the question is, like, if we're able to do parallel distributed processing in this platform, then can you do this faster than just picking up all the data and moving it like over the network? So these NICs aren't cheap; they're not great. And in the case of say NetCDF, where you're like quite literally scanning a lat table and long table, like we're literally going to move that scanning into the SSD itself. So the tables, when queried, like aren't even going to touch the host processor alone, let alone have to go over the network. The fact that we can take large models and they're distributed like 100 ways, like if you had a high performance node that had to receive everything, you're going to have an incast problem of all that data hitting one, like hitting some limited number of end clients. We can, for a lot of these basic filtering operations, we can filter like in the processor like very quickly. I mean, a lot of these basic operations are incredibly parallelizable and small. The problem is there's just so many of them. And if you take the number of cases where like Los Alamos has a lot of this, but like their region of interest is like under 1%. So way back in the day, like there was a term for networking, which was dealing with like if you have congestion and losses or whatever in the network, and they called it good foot. It was a ratio of useful bits on the wire. And normally it was because you had some data loss that meant that the data wasn't useful. And I think this is like an application level good foot, in that you could pick up and send the whole data, but even if you could, the fact that you're sending 100 times more content to like a choke point that has to filter and analyze the data. And like you can throw lots of networking at it, but the costs do add up. And the bottleneck in many of these high performance computing facilities is like the actual networking and the spine to move all this content. And if you have a processor, like not in the HPC community necessarily, but in a typical data center, you tend to have 20x the bandwidth, like a PCI connectivity of like SSDs and whatnot to a host as you do network bandwidth out of that host. So you effectively, if you can process it in a typical data center, it's typically 20-to-1 to get to that first hop wire. Like in an HPC facility, I think the ratio is closer to like 3 or 4-to-1, but there's still a significant choke point of the data from drives to even get to the network link. And if we can pre-filter data from the drives themselves in a distributed manner, and then for things which we could do a further reduction, like a regrid in a GPU, then this means the data that's going over the network is much more curated and actionable.
Really answer the question.
Okay.
The question was a very specific numerical measure. The reduction in time to do an N/M transfer from storage to nodes.
Yes.
Processing versus time to do the processing in the storage.
You can't even the network link can be the network links can be fully booked. Like we can reduce the data going on the wire over an order of magnitude. It will,
But if it takes that much time to do that filtering, then it's not worth the operation.
yeah,
This is a shared resource, and the last thing that you want to do is to push operations there that occupy more of storage than pulling the data out of storage, as far as the network connection is concerned. So that's really where my concern always comes in on these kinds of solutions, is that anything that you push into the storage devices and the storage infrastructure has to reduce the amount of time that it would have taken to just move the raw data.
Sure. Sure, but like we'll be able to filter. We will be filtering at line rate the data can be retrieved from flash in the drive itself. Like it will simply not be possible. Like even if you had a NIC connected to every SSD, like to move 100% of the bandwidth, like you simply can't. Like we will have the filtered result at the same rate that it would be possible to move it if your ratio of NIC bandwidth to SSD bandwidth was 1-to-1. Like we like. So if your compute speed at the compute node was infinite, we will be faster by an order of magnitude at least. Happy to follow up and explain.
Any other questions? It's another day.
I don't know.
Am I good? Oh, is there questions?
Oh,
Was there anything?
the screen was shared. Fix it.
Oh,
Jay wants to. Thank you.
sure.
Thank God.